So this is a talk about storage devices. Okay, and I was chief technologist at Seagate Technology for years, putting stuff into various storage devices. And so one problem that I think is a really interesting one for telling us a little bit about how the brain works, and that'll be the purpose of this, is I would like one storage device to speak English to the other storage device, the other storage device to then be able to answer questions about what it learned from the first storage device. And what I'm going to show you is that kind of architecture has been thought of and has been understood at one level. And I'm going to show you how you can do it. This has very much to do with what Gary was talking about yesterday in terms of the looking at what to measure in the brain to sort of see whether we can capture some of the more sophisticated behaviors. So I'm going to argue, and I've said this to others, that human language and visual perception, really human language, is a window on the universal cortical algorithm, whatever that is. And my argument is that if you want to see the algorithm, understand natural language. You'll see it in operation. So the idea is that language was really developed to allow one neocortex to talk to another in the simplest possible way. Okay? And so if you look at language, you're actually staring at the neocortex and other little pieces of the brain going off. So I'm a student of the Organization of Human Memory. That's where I got my PhD and so forth and so on. And this is a talk I gave at CMU, so this is not 1 hour. There are several studies. One was a study I published in '73, another in '85, and then there was a landmark piece of work, a PhD thesis by a guy named Doug Rohde, who's now left for Google, never to come out of the hallowed halls of Google. And so all there really is his PhD thesis, which is a great read. So the main thing that I've been arguing for dozens of years is human recognition memory reveals a lot about cortical processing. And the study of action perception is a huge gap in this, and we'll get a little bit into this. And language is a window on how we perceive multimodal actions. My original studies all had to do with multimodal activity that was going on and understanding how one modality affects another modality in terms of memories. So the main constructive idea of this little talk is how to train up a very large-scale multimodal system. So if at the end of this y'all see that somebody has done it, okay, this is amazing, okay, then that's sort of cute. So the original study had one result, and it said that it said, and we demonstrated this experimentally, your visual memory system will depend on your language memory system when it can. In other words, language, another part of the brain, will affect visual memories when it can. This is a crazy result. It's showing a multimodal effect that's going on inside the brain. And I won't go into the study. So in '78, something like that, I've been programming since 1967. I published a paper, some work that I spent about 5 years doing on what we called action perception. And here there's a very interesting history of action perception. A guy named Eisenstein, so this is a Russian director, invented something called a theory of montage, which is how do you make a film. And what he said was that in any continuous reel of motion, okay, there are natural points where one action begins and another one ends, or actually these are points of action definition, where actions are defined to the human being. And that actually accounts for why you could make a film with cuts. Because when you watch a film, the camera angles are changing, the light's changing, you're going to another city in a frame. And yet, if the film's done right, the person never notices that his visual field is being destroyed constantly. He's just watching the film. He thinks it's great. He's following the visual activity. Everything is great. Okay. And so if you go to UCLA Film School, they teach this. They teach proper editing of films, when to cut the film. And the instruction is really simple. When an action is defined, when you see an action, cut it right then. Okay. And you give the option to cut the film anytime you want to, as long as you're cutting it when actions are defined. So this is a hugely important thing. It's extremely well studied. Y'all are just not in the right discipline to know it. Okay. There was a guy named Darren Knutson and other people, other researchers, that did what are called breakpoint studies, where they had people watch continuous motion and hit a button every time they saw an action. So they were actually doing what film editors do, but people were tracking where people were pushing the button. And there's the rate of breakpoints, the rate of pushing the button. If there's a surprise in the motion in what you're watching, the person will start more finely seeing motion. He'll more finely seeing action. If you take somebody who's an expert in basketball, who really loves basketball, and he really knows it, and you sit him down and do the actions in basketball, they're very sparse. Only every once in a while does he push the button. He says, that was an action. Okay. Everything else was garbage. Okay. So, one of the things that Knutson did, this is 40 or 50 experiments, was he would have the people write down what they saw after they pushed the buttons. Okay. And they had this beautiful memory. They could write down in detail what they saw. And the crazy thing, he gave me all of his data, and oh my God, okay, where they were pushing the buttons corresponded to English sentences that they were putting out. Sentences and clauses. So language that what they were perceiving visually was mapping directly to natural language. It was crazy. Okay. One of my arguments for why language is an interesting thing here as a window is it's sort of telling you, well, wait a minute, a sentence is kind of a primitive thing. Okay. And when you're just looking at constant motion of something, but that's not what people do. People actually break up the world into things, and then they can describe them in English. 99.9% of all verbs in English and in any other language in the world are action verbs. They're made for describing actions. So I did a little study, and I won't go into this much. I'm giving the slides to let's see if I can. So it turns out I did a study where, well, one of the things to realize here is that actions tend to be organized hierarchically. So here is an action where the large triangle hits the small triangle. Here are the sub-actions for it, and you could either break point, say these are all actions separately, or you could just say that's an action. And so if you look at the actual data, you'll see that people are hierarchically cutting up everything. And there are crazy places where everybody agrees in this 1 second interval there was no action at all defined. Crazy stuff. This is the original Hyder and Simmel film showing that with cartoons, you can get fully descriptive action. You can get unbelievably good descriptive action out of something as simple as a cartoon. You don't have to be able to see a tank moving along the desert, okay, to start beginning to understand how to build these kinds of systems. So I built a system that basically this is all on IBM cards, UTexas Lisp, okay, which automatically composed all the propositions that were being observed, all the stuff, and then a system that would do this kind of action recognition business. But now what I want to get to is Rody. So what I was doing there was building a multimodal system. It was doing visual recognition, and then it spoke English at the other end of it and described what it saw. So Rody came along, and he did a bunch of things, but the main thing was to build a system that could read sentences, English sentences, and then answer queries of the English sentences in English. So it was English in, English in, English out. And the way he did it, and I want to see if I'm going to go fast on this. Let's see. So here he developed a subset of English. He called it Pinglish. And here's some sentences in Pinglish. A answer involves a nice school. The new teacher gave me a new book of baseball. Birds find you felt that lawyers put the big car in the school quickly. Okay. And the question he might ask would be, who put the big car in the school? You feel it was lawyers. Okay. So this is it. This is the richness of the language that he was taking in, and the richness of the questions he was asking and the kinds of answers he was getting. This is sort of the grammar. And out of it, you could develop propositions that were semantic units. And this is sort of Rody's whole network. This is a big backprop system like Randall was talking about yesterday. This is Rody was in psychology the same place Randall was at CMU. And so here's propositional input. Here's a propositional response to a Gestalt query from a propositional query. So this is pure propositional input, and propositional input. Okay. Down here is sentences. This is where the sentences were heard and so forth and so on. And this is the typical hidden layer that joins the language production from the propositional reasoning part of the system. The new sentence on average had 6 propositions. It's all backprop. So this is him training the reasoning system, where what he did was he had input propositions in a sentence, input queries, propositional response, and this is the backprop training bit. And what he did was he trained this system independently of training the other part of the system. So he trained the system in parts. So there was the dreaming, the propositional reasoning stuff. That's it. Okay. And this is the motor stuff. Okay. This is understanding English, producing English, and so forth and so on. Okay. And he trained that independently based on stuff that was coming through the message system. And obviously he was forcing some output. So he trained it The size of the training set, he trained on 4 million Pinglish sentences. It took 3 continuous machine months to train this thing up. Okay. And then he tested it on 50,000 sentences the thing had never seen to figure out how accurate it was in answering questions about the sentences that had never seen them. Okay. I'm not going to, so the hit rate was 70, 80%. This is a really good hit rate. How many of y'all know Rhodey's dissertation? I'm just sort of curious. So Randall did, yesterday I said, do you ever know Rhodey? And he said, oh yeah. Extended modal networks, Rhodey's, my argument is to tell stories, don't do isolated sentences. Okay. And you can then, I like animated cartoon. It gets rid of all the computer vision problems. But what I'm going to do is show you how to extend it to include action perception. So now watch a movie, okay, and answer questions in English about it. That's a neat problem, okay. I would love to have a storage device that you can just feed the movie to it, and then it says, oh yeah, I saw this movie on Turing. It was great, okay. And I look at, just from a pure storage guy's perspective, I would love to take a terabyte of English, okay, or natural language stuff, okay, stick it into a drive and have the drive tell me what all that terabyte was about, okay, in English, okay, or if I speak German. By the way, these are all linguistic universals. Everything we're talking about here are linguistic universals. But this is just the modification of Rhodey's basic network. So you've got the word input comprehension, the business of being able to answer questions, action perception for visual input, sort of a cartoon generator. You had a sentence generator, a story generator. You add a few components to it, and now you should be able to train up a system that can both listen to English, answer questions about what it heard, okay, watch a movie, answer questions about what it saw, okay. But what's critical here is this guy here, the propositional system, which, by the way, fellas, okay, is the basis for all formal logic, right? It's the basis of logic, okay. So there's a strong argument to be made that causality, which is how we perceive the world, causality and intention, it's really a short jump from that domain into formal logics that we see that people can reason about. So mathematics is sort of a reduced version of natural language in some way. So I've been trying to get this funded for 30 years, okay, arguing that by the way, no success whatsoever. Nobody believes me. Surveillance and narration engine, which is DMZ, put a big camera up, watch the troops on the other side, and then in English describe to the guy who's holding the gun what's being seen out there. Okay, be a nice little system to have. And my argument is it's easier than it looks. And then there are lots of problems with the thing. There are some technical issues and so forth and so on. So, and this is the hierarchy business or hierarchy business, the higher order, which bird, which action, which person, low order, things like opposite, subject, predicate, object is an action, so forth, cause. And I won't go into more of that. Yes, so that's it.
So maybe time for a question while Jeremy sets up.
Hi, thank you for talking. I had a question about conventionalizations of English as opposed to other languages which might be more formally defined. They might have like a context. You mentioned
Hello? Okay, cool. About referring to language universals, I was just hoping you could further explain that.
So in linguistics, there's this notion of language universals. These are natural languages, okay? The attempt by man to create an artificial language that is spoken naturally by people has not been successful, okay? It's, it is easier to do real languages than it is. Now, you can do a subset of the grammar, which is what he,
Sure.
but it's easier to do natural language because then at least you have a hope of seeing what's going on in the brain a little bit, okay, of modeling something that's real, okay. Doing formal languages, obviously that was tried in AI years and years ago, okay, general problem solver, stuff. But the argument of people like me who train in linguistics is stick with natural language. It's a lot easier, believe it or not.
Sure. I was just wondering why you chose like English over, say, German.
Oh, I speak English.
Okay.
So does Rhodey.